right, let's start by looking at end behavior of some graphs and looking at their leading coefficients and their degrees. So in this first equation, we have a leading coefficient of 2 and a degree of 4. And from the picture, we can write our end behavior. We know as x goes to positive infinity, f of x, remember this is your arrow on the right-hand side, and that arrow would be pointing up. As x goes to negative infinity is the left side of the graph, and that side is also going up. In our next one, we have a leading coefficient of negative 2 and a degree of 4. Our end behavior, as x goes to positive infinity, f of x is going towards, since the right side is going down, f of x is going towards negative infinity. And as x goes to negative infinity, our left side, f of x, is also going towards negative infinity. In our next one, we again have a leading coefficient of negative 2. This time we have a degree of 3. And our end behavior, as x goes to positive infinity, f of x is going down, so negative infinity. And as x goes to negative infinity, on the left, we're going up, so f of x is going towards positive infinity. And in our last example, our leading coefficient is 2, and our degree is 3. As x goes to positive infinity, f of x is also going to positive infinity. And as x goes to negative infinity, f of x is going towards negative infinity. Now, at the beginning of the year, we only looked at end behavior based on what the graph showed us. And you can actually tell what the end behavior is from the equation without graphing it. So let's look at some generalized rules. First, let's take a look at if the leading coefficient is positive. So that was the first example and the fourth example. What do you notice that their end behaviors have in common? What was the same about their end behaviors? Hopefully you said that as x went to positive infinity, both of their f of x's were going positive. So the right-hand side of the graph was pointing up for both of those. So if you have a positive leading coefficient, you know that as x goes to positive infinity, f of x will go to positive infinity. So let's look at the ones with a negative leading coefficient, our second and third ones. What do those two have in common? They both have that as x goes to positive infinity, f of x is going negative. So as x goes to positive infinity, f of x goes to negative infinity. So what this is telling us is our right-hand side of the graph is going to follow the leading coefficient. Let's take a look at our odd degrees. So the third and fourth example. What do you notice about the ends of those? In both of those examples, if one side was negative, the other side was positive. Or this one, the first side was positive, so the second side was negative. In all odd degree functions, so if the degree is an odd number, the ends go opposite directions. So if it's odd, think opposite. You might be able to guess what we know about even degree functions, but let's take a look. Both number 1 and number 2, their degree was an even number. And what do you notice about their ends? Their ends go the same direction. So let's try and write the end behavior for these without looking at the picture. So number 1, our leading coefficient is positive, and our degree is even. So if it has a positive leading coefficient, we know as x goes to positive infinity, f of x goes to positive infinity. As x goes to negative infinity, f of x goes to, since the degree is even, we know the ends go the same direction, so since the first one is positive, the second one is positive. Our second example, the leading coefficient is a negative number, and the degree is an odd number. Since the leading coefficient is negative, we know as x goes to positive infinity, f of x is going to go to negative infinity. As x goes to negative infinity, f of x goes to, since the degree is odd, we know the ends are going to be opposite. So since this one was negative, this one is positive. Our third example shows one written out in words, and sometimes the SOL likes to put it in words instead of symbols. I like the symbols better because it's shorter, but this still could come up. So as x approaches positive infinity, that means the same thing as x approaches positive infinity. Here we have a leading coefficient that's negative and a degree that's an odd number. So since our leading coefficient is negative, we know f of x is going to go towards, and we're just going to write it out in words, negative infinity. Since the degree is odd, we know the second end is going to be the opposite of the first, so that one has to be going towards positive infinity. And if we wanted to check our answers and make sure it lines up with our pictures, we could use the graphing feature on our calculator to plug these equations in and take a look at the graph and make sure the ends do what we thought they would do based on our leading coefficient and our degree. All right, next we're going to talk about multiplicity. So below is the graph of f of x equals 1/10 times x minus 2 times x plus 1 squared times x minus 4 cubed. So the real roots of the polynomial, we can get them from our factors or we can get them from our graph, but they would be -1, 2, and 4. The multiplicity comes with the exponents on their factors. So x minus 2, what exponent does that technically have? It has an exponent of 1 when it's not written there. So 2 has a multiplicity of 1. -1 has an exponent of 2, so it has a multiplicity of 2. And 4, the factor with the 4 had an exponent of 3, so 4 has a multiplicity of 3. Multiplicity just technically means that this root comes up more than once, or twice, or 3 times. So what does the graph look like at each root? At -1, what shape does this make? It looks like a parabola, or the shape an x squared makes. 4 makes this shape. What do we know makes that shape? Looks like a cubic. X cubed. And if we look at just the part where it crosses at 2, that looks like a line, which is represented by an x. And if you notice, -1, its factored had a 2. It looks like an x squared. 4 had an exponent of 3. It looks like an x cubed. 2 had an exponent of 1, and technically x is an exponent of 1. Now the degree for this polynomial, we need to check first, is this written in standard form? No, remember, standard form doesn't have any parentheses, it just goes highest to lowest exponents. If we were to multiply this out, we would have x minus 2 times x plus 1 would be there twice, and x minus 4 would be there 3 times. So we would have 1, 2, 3, 4, 5, 6 x's, so the degree is 6. 1 plus 2 plus 3. And a way we can check this degree is even. Are our ends going the same direction? We're probably on the right track. So let's look at another graph. Here we have the graph of x to the 4th minus 14x cubed plus 70x squared minus 150x plus 125. What are the real roots of the polynomial and their multiplicity? Well, it only touches the x-axis once at 1, 2, 3, 4, 5. So 5 is our root, and it has a multiplicity. We can tell its multiplicity by the shape that it makes when it touches the 5. So since it makes a parabola shape, we know it's like an x squared, so it has a multiplicity of 2. Based on the fundamental theorem of algebra, which we talked about last class, and remember that means that the degree of the function is the greatest number of roots that we can have. So since we have a degree 4, we know that this polynomial has 4 roots. Since the 5 had a multiplicity of 2, that counts as 2 of the roots. So if 2 of the roots are taken care of by the 5, and it doesn't touch the x-axis anywhere else, that means that the other 2 roots are complex. So the multiplicities plus the number of imaginary roots needs to add up to 4 roots. That's all for today. See you in class.